paradigm shift in determining Neoproterozoic atmospheric oxygen. We present a new and innovative way of determining the oxygen level of Earth's past atmosphere by directly measuring inclusion gases trapped in halite. After intensive screening using multiple depositional, textural, fabric, and geochemical parameters, we determined that tectonically undisturbed cumulate, chevron, and cornet halite inclusions may retain atmospheric gas during crystallization from shallow saline, lagoonal, and/or salt pan brine. These are the first measurements of inclusion gas for the Neoproterozoic obtained from 815 plus or minus 15 million year old brown formation chevron halite of the Officer Basin in southwest Australia. The 31 gas measurements afford us a direct glimpse of the composition of the mid to late Neoproterozoic atmosphere and register an average oxygen content of 10.9%. The measured PO2 puts oxygenation of the Earth's paleoatmosphere roughly 100 to 200 million years ahead of current models and proxy studies. It also puts oxygenation of the Neoproterozoic atmosphere in agreement with time of diversification of eukaryotes and in advance of the emergence of marine animal life. Introduction. Deciphering the oxygenation history of the atmosphere and oceans is critical to understanding weathering processes, sedimentary environments, climate change, mass extinctions, tectonic events, and the evolution of Earth's biota. Earth's atmosphere was not always plentiful in free oxygen, and finding a paleobarometer to measure its partial pressure over geologic time remains a famously difficult challenge. Accurately defining Archean, Proterozoic, as well as Phanerozoic atmospheric conditions remains problematic despite the multitude of proxies from marine and non-marine archives for modeling atmospheric conditions. Indeed, according to Canfield, the sparse geologic record combined with geochemical uncertainties yields only a fragmentary and imprecise reading of atmospheric oxygen evaluation. Major steps in unraveling the evolution of atmospheric oxygen and its close link to the evolution of life on Earth have produced some revolutionary hypotheses and concepts. In 1998, Canfield suggested that the deep ocean of the mid-Proterozoic was anoxic and ferruginous, and atmospheric oxygen was less than 0.1%. However, much remains to be quantified about the redox state of the Proterozoic ocean and atmosphere, and especially the emergence of marine animal life during the Neoproterozoic. The increasing number of elemental and isotopic proxies gives us a better understanding of the relative redox state of the atmosphere and ocean during Earth's early history, which shows that most of it was marked by low oxygen levels with two exceptional perturbations, deemed the Great Oxidation Event, GOE, and the Neoproterozoic Oxidation Event, NOE. The models of earliest oxygen evolution document the GOE, but are quite uncertain about the NOE and its relationship to the diversification of plant life and the evolution of marine animal life. Several models suggest persistence of extremely low oxygen levels for this time period, whereas others advocate a more moderate and increasing but uncertain levels. Most of these models leave unresolved the question of whether oxygenation of the atmosphere-ocean drove animal evolution or animal evolution drove oxygenation. Halite is well established as a paleo-environmental archive through analysis of fluid trapped in inclusions. This archive with primary fluid in inclusions is now accepted to stretch back to the Neoproterozoic. Inclusions in halite may contain two phases consisting of primary evaporate brine and a gas bubble. The gas may reflect the ambient atmosphere, gas trapped in soils/sediment columns, or gas incorporated during diagenesis. It is our intent to demonstrate that trapped gas in halite is primary, and then measure the inclusion gas to document the actual oxygen level of the Neoproterozoic atmosphere. Preservation criteria. Geologic archives, irrespective of material, whether used for proxy investigation or direct measurements, needs to be intensively screened for their preservation state, including our material of choice in the study, halite. We present a number of features and parameters that halite must possess to be considered a robust archive for retaining primary gas contents. Halite from highly concentrated brine starts by forming cumulate crystals at the brine-air interface as floating individuals or rafts. These crystals will include bands of inclusions acquired during rapid growth, but they eventually settle out into the bottom of salinas, playas, or subclases of shallow water depth. Intermittently wet syntaxial precipitation of halite initiates the formation of chevron and/or cornet crystals. Chevron halite forms rapidly on the cumulate substrate of the air-brine interface as vertically oriented and elongated crystals with fluid inclusion-rich and milky chevron bands aligned parallel to the crystal faces. With faster growth, more square to rectangular inclusions may form along the crystal faces and upward pointed cubes in continuous and extensive beds form. Another type of halite that forms on the cumulate substrate at the air-brine interface are cornet crystals with increasingly widening upward-oriented inclusion bands. The inclusion bands tend to be parallel to the crystal face and more abundant during rapid daytime growth. In addition, patches of clear halite might be associated with chevron and cornet halite during primary growth, but with the exclusion of inclusions. Halite may also form at subaqueous depth, producing few to no inclusions from stratified, dysoxic, anoxic bottom water. Overall, the original halite crystal fabric must be devoid of any depositional and/or post-depositional tectonic and/or halotectonic folding, faulting, and fracturing to allow the preservation of bedding and crystal fabrics and textures. Recrystallized or diagenetically formed halite may be identified by unusually large, distorted, sporadically distributed, interlocking mosaics of clear crystals with large and abundant inclusions. Halite cement forms during early burial, and the entire process is complete by roughly 45 meters depth, and afterward, halite is no longer susceptible to dissolution and alteration except under high-temperature fluid burial and tectonic conditions. Geochemistry may be an additional screening tool to identify the primary state of inclusions in halite. Bromine and delta S34 are two such tools to ascertain the primary and marine nature of halite. The sulfur isotope composition is largely controlled by the sulfur content of the ambient but geologically variable seawater, whereas bromine content will range from 65 to 75 parts per million at the onset of halite crystallization, depending on the partition coefficient, and reach roughly 270 parts per million at the offset. Also, the major ion chemistry of the inclusion fluids reflects the preservation potential of the halite. Maturation of halite deposits is generally complete within 45 meters of burial, manifested by the occlusion of all intercrystalline porosity by clear halite cement. Halite fluid inclusions may contain oxygenic photoautotrophs, such as Dunalilia and halophilic archaea, with the former potentially increasing the local oxygen concentration. Halite forms in brines with greater than 325 grams per liter salinity that may be replete with halophilic bacteria, imparting a red color on the water, but lack live oxygenic photoautotrophs. Thus, local post-depositional oxygen production within inclusions is not an issue. In summary, if depositional conditions and fabric, textural, geochemical parameters support a primary state, then gases trapped in inclusions of cumulate, chevron, and cornet halite may contain gas reflective of the ambient atmosphere at the time of crystallization. Analytical method. Halite was cleaned with isopropanol to remove surface organics and air-dried, and then placed under vacuum overnight to remove interstitial and intercrystalline gas. A sample consisted of several match-head-sized halite pieces that were crushed incrementally to produce 5 to 12 successive gas bursts. Data acquisition was performed with 2 quadrupole mass spectrometers operating in crush-fast scan (CFS) peak hopping mode. The instrument was calibrated using Scott gas mini-mix gas mixtures and verified with capillary tubes filled with gas mixtures, and 3 in-house fluid inclusion gas standards. Amount of gas was calculated by matrix multiplication to provide quantitative results. Volatiles are reported in mole percent, and the 3 sigma detection limit for gases is roughly 0.3 parts per million. The gas results of the capillary tubes cluster close to the global atmospheric gas content, and they clearly demonstrate the robustness of the CFS-MS method for measuring gas in artificial and natural inclusions. All results of laboratory tubes and modern Messinian, Cretaceous, and Neoproterozoic halite samples are presented as water-free and large gas burst-free data. Some halites produce steady gas burst trends that support their homogeneous nature and constant environment of crystallization, whereas those with some variability reflect some unknown influences that require more study. However, at this time, we overcome that issue by using only averages in our evaluations. Figure 1. Limitations. Obtaining well-preserved halite with abundant gas inclusions despite intensive screening is a challenge. The need for only small inclusions may be a benefit in that area with cumulate, chevron, or cornet features may be exhumed from large halite crystals for gas analysis. However, Small inclusion size and corresponding low gas volumes may hinder their 100% extraction, and indeed oxygen extracted from one modern cumulative halite, Carlsbad, relative to the atmospheric composition, is lower by roughly 9.2%. More study is warranted to evaluate this observation and its potential impact on ancient halite-based oxygen measurements. Method evaluation. The initial consideration is the testing of gases obtained from inclusions of modern and ancient cumulate, chevron, and cornet halite to verify the robustness of the archive. Modern halite. Modern halite for testing the oxygen paleobarometer were recovered from ponds at the Mosaic Salt Mine near Carlsbad, New Mexico, and Lake Polaris, Southern Cross, Australia. The material consisted of rafts of cumulate halite growing at the water-atmosphere interface of the ponds, and their inclusions were tested for N2, O2, and argon gas contents. The results fall within acceptable parameters of modern atmospheric air. Messinian halite. Material from the latest Miocene was obtained from the Racalmuto mine of Sicily. Based on its fabric and texture, the halite is of the cornet variety with bands rich in inclusions and precipitated at the water-atmosphere interface. Its gas contents overlaps significantly with those of air standards and modern halite from Carlsbad. This suggests little change in atmospheric oxygen over the past 6 million years. Cretaceous halite. Material from this period covers a time of controversial atmospheric oxygen gas contents. Chevron halite from the Cretaceous Meng formation of Tibet gives average oxygen of 25.8%, which is higher than the modern level, 20.946%, and supports the assertion of elevated PO2 during the mid-Cretaceous. It is highly unlikely that oxygen could have been injected into halite inclusions without evidence of morphochemical disruption, and we must conclude that Cretaceous atmospheric oxygen was most likely higher than present-day levels. The tests performed on the modern Messinian and Cretaceous halites support halite's robustness as an atmospheric oxygen archive. Neoproterozoic halite and atmosphere. Our Neoproterozoic halite samples are from the Empress 1A and Lancer 1 drill cores from the Officer Basin, southwestern Australia, a broad marine shelf tectonically stable since Neoproterozoic time. The samples at the two localities are from the B interval of the Brown Formation that is bracketed to 830 to 800 million years ago based on chemostratigraphy and geochronology. In summary, the halite samples were screened for their preservation using petrography, chemistry, and stable isotope compositions. And Table 1 summarizes the fabric and geochemical parameters. The Neoproterozoic halite inclusion gases are all oxygen depleted relative to modern atmosphere. Inclusion oxygen from sample 1478, the Empress core, is low at 1.64%, and based on depositional and geochemical features, the halite formed in the salt basin during rising water levels and in dysoxic bottom water. In contrast, The other halite samples from the Neoproterozoic brown formation are replete with bands rich in fluid gas inclusions. CFS-MS analysis of inclusions show average oxygen contents ranging from 10.15% to 13.43%. Thus, atmospheric oxygen during the mid-Neoproterozoic was on average 10.9%, or about half of the modern level at 20.95%. Discussion. Gas analysis in halite has evolved from methods requiring large samples with large inclusions of low resolution to methods of heat or cold extraction, CFS, and measuring by mass spectrometry requiring smaller samples with smaller inclusions of much higher resolution. 3 models of atmosphere and ocean oxygenation place onset of the NOE somewhere between 500 and 800 million years ago. The first model is essentially unidirectional, with 2 major step increases in both atmospheric and oceanic oxygen. The second model offers up a more gradual and uncertain increase during the mid-Neoproterozoic. And the third model, espoused by Canfield, expresses a greater degree of uncertainty during the Neoproterozoic oxygenation. Our measured average atmospheric oxygen of 10.9% is well above levels of all major models. The atmospheric oxygen contents and commensurate levels in seawater proposed by the models are too low to sustain the emergence of animal life, and increases in oxygen postulated for the late Cryogenian and mid-Ediacaran are too late to trigger the emergence of marine life. Instead, our measured levels of oxygen for the mid to late Tonian, Neoproterozoic, atmosphere is more than sufficient to support the expansion of plant life and facilitate the emergence of marine animals. Furthermore, our atmospheric oxygen measurements infer that the NOE took place at least 200 to 100 million years prior to that suggested by most models based on proxies. Conclusions. We provide the first direct measurements of the oxygen content of the Neoproterozoic atmosphere. After extensive and careful screening of ancient halite crystals, our analysis of Neoproterozoic halite inclusions and their gases sealed during crystallization confirms that the average oxygen levels, roughly 815 billion years ago, were 10.9%. Our atmospheric oxygen measurements indicate that an oxygenated environment in which complex life could have emerged and flourished in advance of the Ediacaran and Cambrian explosions. Our direct analysis of gas-bearing inclusions in halite places atmospheric and shallow ocean oxygenation roughly 100 to 200 million years in advance of most proxy-based models. Inclusion gas analysis of primary halite is a new and novel paleobarometer of atmospheric oxygen with many potential terrestrial and extraterrestrial applications. Figure 1. Ternary N2 argon O2 diagram of inclusion gases from our laboratory capillary tubes, air standards, and of modern and ancient halite compared to modern atmospheric contents. Contents are based on averages for each sample. Figure 2. Setting of Officer Basin in southwestern Australia showing locations of Lancer 1 and Empress 1A drill cores and sampling horizons in Brown Formation, modified from Spear et al. 2014. Figure 3. Thin section view of halite sample 1502 from the Empress 1A core, Officer Basin, Australia. Undisturbed chevron bands with gas fluid inclusions are clearly visible in photograph. Upward crystal growth is in direction of chevron tip, and geochemical concentrations are in parts per million. Figure 4. Atmosphere and oxygenation trends during Neoproterozoic. Dashed line is the proposed atmospheric oxygen trend by Canfield, 2005. Red unidirectional curve represents the traditional viewpoint, Klump, 2008. And the blue curve represents emerging models presented by Lyons, 2014. Greenfield shows our atmospheric oxygen measurements for Tonian time during Neoproterozoic, Table 1. C. Cambrian, O. Ordovician. Table 1. Geochemistry of halite, bromine, delta S34, and extracted fluids, sodium, calcium, magnesium, chloride, and oxygen gas contents of Neoproterozoic brown formation, halite, Officer Basin, Australia, and modeled geochemistry of Neoproterozoic seawater, modern seawater, and atmosphere.